All right. As for today, all right, gonna work with chapter 3, and then we have an exciting test next time.
Oh, yeah.
And also remember that. So I know it says start at 9:30, but we're gonna start regular time, and then but don't be pressured. We'll go till noon plus.
Okay.
So I was like, worst case, we might have to move the room, but like that's definitely not gonna be an issue.
Cool.
As for today, so we were in the midst of looking at reduction of order problems. And so the big thing about these is we have our Cauchy-Euler formula. We're only going to look at equations of this form. And we're given a solution, and then we create the second solution from the first. All right. Since they are Cauchy-Euler, the one solution is always a multiple of the other. So our standard idea is we let y2 equal some multiple, some function of y1. In this case, that means we have v t. All right, since y1 is t, all right, and again, that is v of t, but since we need to do what, it's easy, it's better to write it as v. What do we have to do a few times now?
Derivatives.
Derivatives, right? So then we're going to plug all those y2s into our differential equation. Plug all that in and simplify it down a little bit. And these should always end up in this form, all right? So there's one in the home fund that I distinctly remember doing that has some real algebraic fun. But the idea is they should always end up in this form. Because the whole idea when I look at this, all right, I see a second derivative and a first derivative. Notice what's not here anymore. What's missing now? Second derivative, first derivative?
Regular.
Yeah, no derivative, just the function itself. Because this, every time, implies this is the reduction of order part of the problem. Because this is the definition, right? The very first, one of the first definitions we learned on day 1 was order. That is the power of the differential equation. So we're trying to reduce the order. Well, so we're going to let W equal V prime, and of course, W prime then equals V double prime. And then we have Josh's favorite function, which is
linear ordinary differential equation. First order.
and right as we've seen repeatedly, most important part about differential equations,
Standard form.
form. What I was like, yeah, whatever. I was like, standard is a weird way to say it because I was like, it's the form. Is it standard across all of them?
No.
No, it's what form for
Or
that
style
one,
of
right? Yeah, like
solve core solution.
yeah, and then we can solve. But so form is everything. And what's the form for your favorite differential equation, Josh? What's the proper form?
Y prime minus something of like y of x or x of
what,
y t equals.
what needs to be adjusted?
We need to subtract or get y prime by itself, not y prime, the w prime by itself.
Yes, w prime needs a coefficient of 1. Yes, absolutely correct. Sorry, I'm picking on Josh. Lane, you were down with that, okay?
Huh?
Not me picking on Josh. You understand what's happening too.
What?
And already, right, once we get it into the proper form, I see all kinds of good stuff because the integrating factor is going to be ln, and that goes away. So all kinds of easy. T to the fourth, basically, is what it's going to look like, right? So we could solve that down, but we're pretty good at solving first order linear simple differential equations. Once again, I got to W, right? That was all of this, all right, is we do all these reduction of orders and all these substitutions, we get to W, and then once I'm at W, I finally reached the pinnacle there, and then we have to go back to V to then get to Y. Absolutely correct. And we talked about it last time, right? We keep adding all these constants, but be aware, all right? I'm adding them only out of completeness, right? You can dump it immediately, even at the W step, all right? You find this and you can drop that constant immediately because all we really care about, all right, is what's happening to our variable of interest in this case, which is T. Which means the only thing that actually matters is T to the -3. Because what we actually wanted, y2 of t, which was v of t, y1 of t, t to the -3 times t, which of course then gives us t to the -2. Which gives us the general solution, y of t equals c1t plus c2 t to the -2. Because all of that is to get down to be able to do reduction of order on the differential equation. All right, and again, one of our solutions is going to be what we started with, right? Y1 was given to us as t. All right, the whole idea is just finding our second solution. All right, reduction of order, very, very common method. All right, like I said, I think there's like one home fun where we have to find that initially, but it's given pretty heavily implied when it is. All right, the best part of this chapter. So we busted through a bunch of those solutions to the quadratic of our characteristic equation. And each time I kept saying, it's a nice enough solution, right? Even when I did the proof, I said, let's pick E because, that's going to be nice, all right? The reason is, all right, the Wronskian, all right? This is, at least has some similarities to the Jacobian that you may recall in Calc 3. But the big thing is with the Wronskian, okay, it identifies what we are calling a nice enough solution has a formal definition in differential equations. All right, we're gonna prove that in just a minute. But all right, we have our differential equation of these second order equations that we've been looking at. All right, we have our initial conditions. The idea is, all right, is that when we plug in our initial conditions into our general solution, given the principle of superposition, our two equations look like this, and this is what we've been solving with the matrices. Before I proceed, all right, we need to take a little break and recall some of our matrix algebra. Kramer's rule, right? So we already just did this, right? How are we solving this? What function were we using in our calculator? How were we solving this guy?
RF.
REF, right? Reduced row echelon form. Well, that is, and that's by far my favorite too, right? That's actually a really nice form as long as they are simple row operations that have to be performed. Now, calculator does those all quick, but even in big matrices, actually REF will slow computers down. So Kramer's rule, all right, if you recall, the other form we could write this in is AX equals B form. Kramer's rule takes the determinants, and determinants are actually way faster to calculate. Same process, both Kramer's rule and REF, all right, solve a matrix, all right, of the exact same form, all right? This just uses determinants, and when values get really big, and I'm talking like 10,000 by 10,000 matrices, they tend to actually implement Kramer's rule. Just to identify and refresh on this a little bit, let's look at a little example. So I want to use Kramer's rule to solve this system of equations. So let's put this into matrix form just to remember what that looks like. So AX equals B form. So that means a matrix of A. That's all the values of each column of X's just the coefficients. The matrix X is exactly what it sounds like. And then B is the solution matrix. So AX equals B form. What we should definitely be familiar with. Kramer's rule then uses a bunch of determinants. All right, so we have the determinant of A, which is exactly that. And again, just something else to refresh in our calculator. Where's determinant in your calculator?
Or the matrix button.
Yeah. And then one other.
Oh, you just said your matrix A in it?
Well, I was like, it's technically in the math command. That's all I was meant to say. Yes. But I was like, but yes. All right, go into matrix and then go over to math. And it's the first one, right? Okay. And then you have to put in the 3 by 3 and then DET of your matrix, and you can do this over and over again. Just want to make sure everyone's okay with the calculation. All right, so this guy gets -187. In order to use Cramer's rule, we need to do several determinants. So A1, all right, if this is my matrix A, okay, this is the determinant of A, this is what A looks like. A1, all right, is simply replacing your solution matrix into that first column. A2 would then be put it in the second column, A3 in the third column. So every time, it is just about rotating that -2, 10, 3 into your matrix and recalculating the determinant. So we can calculate all of those, and then Cramer's rule just says in order to find x1, it is the determinant of A1 all over the determinant of A. And it's just yet another way to calculate matrices, right? You can also solve this, right, with inverses, right? Take the inverse of A and x equals A inverse B. So Cramer's rule is just one that you may not have seen. That's all I'm really pointing out here, because this is the concept of how the Wronskian is calculated. All right. So in case you had never seen that, that is yet another way, all right, of how to calculate matrices. You okay with that?
How did you get these values? I'm like kind of lost on
So
on the matrix values. I got that makes sense. I mean, just pulling the coefficients off of.
So I'm simply just substituting this in. It's just the solution. So A1 is this thing.
Times -2.
No, but instead of column 1, I'm putting this in instead. So -2, 10, 3, and then this is the same.
And then next determinant, it'd be
yes,
even the first, replace the middle.
yes,
Okay.
exactly.
Okay.
So notice that,
Thank you for that.
right? -2, 10, 3 is in the first column, and then it's in the second column, and then it's in the third column. That's all that is.
Thank you so much.
It's just literally replacing the solution matrix into each column as we go. So back to our equation. So I can substitute this, all right, and I can do this as two determinants using Cramer's rule. Now notice the big thing about that is that the overall determinant, the one without the solution matrix plugged in, all right, is in the denominator. We know by definition, what can the denominator never be? Zero. So we basically identified a situation that as long as the denominator is not 0, all right, we have a solution for our constants. That denominator piece, all right, is what we refer to as the Wronskian, all right, we write that as W, all right, you see lots of forms of it, FG of T, Y1, Y2 of T, of a value, all right, but most of the time, we use the Wronskian, it's W. This idea then is what we call a fundamental set of solutions. This is what I kept saying, nice enough. All right. So, all right, if I have these two solutions, all right, as long as the Wronskian is not zero, then the two solutions are called a fundamental set of solutions. That's the official terminology. All right. And then we can have the solution to the differential equation. The good news is, all right, we're going to prove a couple of them now. Those three ones that we already saw, they're all fundamental sets of solutions because I was saying, just trust me, they're nice enough, right? And now we're going to prove a couple of those to verify they actually are, all right, nice enough solutions. So back to our complex root solutions, right? We saw that the two solutions ended up being of this form. Right, when we had, right, when the characteristic equation, right, had imaginary solutions. So now I want to prove that is a fundamental set of solutions by creating the Wronskian. And for us, it is literally, because remember, it's our initial condition. So it's literally just the function and then the derivatives. Proving this is actually pretty easy. The only challenge ever comes in with these equations is that the derivatives can be get annoying. And especially in this case, because I have product. And already, yeah, that it becomes a little annoying when you have to multiply that whole thing out. All right, and then we need to recall just the basics. Now, good news, for most of what we're gonna do 2 by 2. So using a calculator is a nice way, but in order to do a determinant by hand, do we recall what you have to do?
Crisscross applesauce. Like,
All right, and remember that it's multiply, subtract.
minus.
Yep. But yeah, that's all it is. So we multiply this guy out. And most of what we're going to be doing is looking at 2 by 2s because we're in second order and hence two solutions. Now, typically I would skip all the details here, but it is kind of beautiful. So I was like, so we can see a couple of important things occurring. What?
That one term, no, that one term cancels out, right?
No, look.
That
I
one.
was like, lambda E2, blah, blah, blah. I was like, sine, cosine, that goes away.
You could factor out the mu, e.
And then it equals one. Sine squared
Oh,
cosine.
because we have the fundamental identity of trigonometry, right? Sine squared theta plus cosine squared theta equals one. So I was like, when we see this, I was like, actually, I see a lot of pretty things right here.
A lot of beauty in the scene right now.
Yeah, I was like, and that's what I'm talking about when I was like the grind. I was like, you have to do so many problems to start seeing that the beauty within the grind. So yes, absolutely, that cancels out, and I can clearly see e to lambda t, all right, which becomes sine squared mu t plus cosine squared mu t. That whole guy becomes one. So we just end up with mu e to the 2 lambda t. And so this is what the Wronskian is. We have to then identify and just make sure. So by definition, mu cannot be zero because the whole thing was that's part of the complex solution. So if that's zero, then this whole thing becomes zero, all right? Which means this was no longer the complex solution to the characteristic. And then once again, with this function, where does this cross zero?
Never.
It never does. So notice what we have. Since mu cannot be zero and e to the 2 mu t is never equal to zero, then the Wronskian, which equals mu e to the 2 lambda t, is not equal to zero. And since the Wronskian is not equal to zero, y1 of t, which equals e. And y2 is a fundamental set of solutions. So, all right, we just proved what we had been assuming up till now. And that's the whole idea, all right? And we can do that. We could do that with all of them. I think I went into all of them. Okay, that's enough. But basically, we had three cases, right? There's three possible solutions for the quadratic, all right? The complex one is the hardest one to show. You could show the other one way easier, actually. But the whole idea is that they're all fundamental sets of solutions. We're going to see, all right, that we have even more than that. This was the Cauchy-Euler equation that we did last time, right? I want to see if these are a fundamental set of solutions. Those, by definition, if we are in those three cases, right, of the characteristic, those are always fundamental sets. Anything else, you need to identify. Because this, we did not start with the assumption this is a nice enough. These are solutions, but I don't know if these are a fundamental set of solutions. So calculate the Röntgen. Simplify that guy down. And we get this equation. So sometimes we have to go back to the initial because at this stage, is there values where this thing is undefined? Bad news? Yeah. Okay. So we really need to identify, I was like, this has a restriction on the denominator. All right. Specifically, I was like, square root. I have a square root and a fraction. For the square root, that's simply just set the underneath. Go ahead. I was like, t greater than or equal to 0. All right, for the fraction part. So I was like, I definitely have some issues with this. All right. This was not told to be, so I have some problems that look like this can't be great. This can't be equal to 0. It has to be greater than or equal to 0, which means the domain restrictions messing up the Röntgen. I need to look back at my initial equations. This is the initial solutions, which means there's a domain restriction on this initial function. Now be aware, I could have done this initially. Me, I never do it until I have to. All right? Because otherwise you'll spend all your time identifying domain restrictions. So I always see, hey, maybe the Röntgen came out to just be 5. Is 5 equal to 0? Nope. Oh, we would have been good. All right. So if it ends up having something, then I need to go back and I need to look at what the initial restrictions, because this is causing me all kinds of issues. All right. So t to the negative 1, which actually is 1 over t. All right, which actually says, what can t not be? Oh, look. This guy, which is, I could also write this as square root of t cubed. Once again, domain. That's square root, t cubed greater than or equal to 0, which implies t is greater than or equal to 0. These two together state that the domain, all right, is what of this function?
Exists when
T is
above
greater than 0.
Yeah, t is greater than 0, right? And I could write that as t greater than 0, or we could use interval notation, 0 to infinity, whatever you prefer. It's all the same. So that actually means I have an initial domain restriction, which means these issues that are making the Röntgen undefined are the issues. No, by definition, t is greater than 0, which means if this entire function is greater than 0, is it ever going to equal 0? No. So since t is greater than 0, the Röntgen, which is 5 all over 2 over t, will always be greater than 0. Hence, Röntgen is then not equal to 0, since that's the only thing we really care about. And y1 of t, which equals t to the negative 1, and y2 of t form. So right? Y1 and Y2 form a fundamental set of solutions. The big thing here, okay, this is one of those detail things, all right, that does matter. We have to make sure, okay, like, because the Wronskian is zero, since the Wronskian is zero, that's why it's a fundamental set of solutions. So that is a wording thing that does matter, okay? There's also, all right, what is called the fundamental set of solutions theorem. This has several names, and in most books, this is called something like theorem 5. It just depends where it is. All right. So this one, you can create a fundamental set of solutions, all right, as with these two initial conditions, all right, whatever your differential equations you have. So currently we have those three that are the solutions to the characteristic, and they're always a fundamental set of solutions. But by using this theorem, I can always create a fundamental set of solutions. It is using these two, all right, initial conditions. So I can start with an IVP. It could say, solve this, and find me a fundamental set. I'd have to solve this first to find the fundamental set of solutions, then use that IVP. But I want to be clear. I explicitly state in the home fund, use the fundamental set of solutions theorem. That means I'm using these two particular initial conditions, because that's what the definition says. It says that we will create a fundamental set of solutions no matter what the second order differential equation, homogeneous equation is. Because, by definition, look at the Wronskian. If I have these initial conditions, oh look, 1, 0, 0, 1, oh, it equals 1, and it is clearly not 0, so this always creates a fundamental set of solutions, because by definition, as long as the Wronskian isn't 0, all right, it is without a doubt, right, 0 and 1, the easiest way to create that determinant, so it is always not 0. Okay, so let's look. All right, I want to use the fundamental set of solutions theorem, all right, to find a fundamental set of solutions for this differential equation. Now, we have to start somewhere, all right? So this one, I could start with this and create it, but I could have done this with reduction of order, but the derivatives already get rough. So I want to create my characteristic equation to at least find my initial values. So I created my general solution. Now here's the part, okay? Now we need to set up. Oh, okay, we need a derivative first. So we create, now using the theorem, we're going to create two initial conditions and solve it both times. So y of t 0, and we were told in our question it's 0. All right, but this could be any number, but in order to make already what is going to be annoying, less annoying, 0 is the best. It's going to be 0 for t 0. So 1 and 0, all right, and 0 and 1. So we solve this twice. And again, this is all because T0 equals 0, all right, but that could be any number. All right, so we solve that down and get C1 and C2. So what we have here is y1 of t. We have to now do this again to get y2. All that gave us was the first piece. Notice that it is almost the same, right? The first one was 1, 0, the second one is 0, 1. So almost the same initial value problem to solve. That gives us y2. So notice what our general solution is. Our general solution is this. This is the actual general solution using the fundamental set of solutions theorem. All right. But by definition, this always creates a fundamental set in which when we do the Wronskian, this will always come out to non-zero. This Wronskian, skipping steps here, would equal Negative 4t, which we've just said 5 times in a row. When is that 0?
No.
Never. I was like, it's not 1.
Never.
That can never be 0. So by definition, this is, and be aware, by using the fundamental set solutions theorem, you don't have to prove this because you used the theorem, all right? It's proved from what the initial conditions are. It will always come out non-zero, just to further emphasize that. Here's the big part though. The general solution was this guy. This is what we started with. Using the fundamental set of solutions theorem, we get this. Which do you prefer?
First one.
Oh yeah, duh, okay? Because it's about 1,000,000 times easier. Is this one valid as well? Yes, all right? Is this just a combination of this? Yes, all right? So the whole idea is that there are lots of other possibilities, okay? And if we're doing our 3 from the characteristic, the ones from the solution of the characteristic are always going to be way, way simpler. And so that's what we're going to always use in practicality. All right. But that theorem is really nice because when you start getting a reduction of order and you're just not sure if those work out, you can guarantee to use this theorem and make, all right, 1 with this theorem. Also, as a note, what in which case do you think is the constants are easier to solve for?
First one also.
Yeah, the first one also, right? So the constants suck solving for this one as well. All right, so just be aware the theorem is there and it is quoted in every single differential equations book out there, all right, as an alternate because you want a fundamental set of solutions and we're not always going to be working with these beautiful homogeneous differential equations. All right, one last big topic related to what we've been doing with all this matrix use. Linearly independent and dependent functions. By definition, all right, the definition of linear independent dependent functions starts with a bunch of constants multiplied by functions and it equals 0. If you can find any non-zero constants, all right, that make that solution equal to 0, they're linearly dependent, right? If you can only find 0 functions, then they are linearly independent. And we like to write this also in matrix form. So you may see this notation as well. Basically, constants multiplied by a bunch of functions, all right? And if you multiply those matrices, right, and it would be a summation, all right, then if it equals 0, linearly, if the only constants are zeros here, then it's linearly independent. If there are any non-zeros, linearly dependent. All right, let's look at some examples. So I want to determine if the following set of functions are linearly dependent or linearly independent. So simple using our definition. We start here and see if we can identify non-zero functions. But it always starts with plug it in and let's see if we can simplify this mess. If I pull out a 2k, right? I'll pull out a 2. Does cosine squared minus sine squared look familiar? Yeah, what is it?
Tangent identity?
Oh, no, easier than that even.
I don't remember.
It's a double angle.
Cosine.
It is cosine. And if you recall, it's also written as cosine this and
Mhm.
all right, so, all right, that is double angle. Which actually means this whole thing I can turn into cosine of 2x. And oh, look at that. Which means I can pull that all the way out. So the cosine is periodically zero, but remember, we're really looking for our constants of c and k. So this really reduces down to this equation. And then basically all I want to do is pick constants. Can you think of a constants for c and k I can put in there to make that thing zero?
You can solve it and do it that way, right?
Well, can't solve this. I have one equation and two unknowns. So it's really just pick, I mean,
Plug and check out, or just,
yeah, well, guess and check. It's really just guess and check, right? So pick a value for C and pick a value for K that's gonna make that thing equal zero. What are the easiest ones without a doubt?
0.
What, not zero.
Sorry.
You're right. Zero is the easiest. What non-zero values? I 100% agree. Zero is the easiest number.
Fractions, like 1, like,
-2 and 9.
See, okay, I think that way, but fractions is the other way. So with I'd say C equals -2, K equals 9, because right, that makes -18 and +18. But you're absolutely correct. There is not just one option here. Okay, the other way to do it is how about C equals 1/9, K equals
-1, or excuse me,
-1/2.
-1/2.
-1/2. Is there a bunch more I could list?
Probably.
Absolutely. Okay. These are without a doubt, I'd say the easiest two, right? And because be aware, I could do it the other way. +2, -9, -1/9, +2, and then we could go ad nauseum. But the idea is that did you find a single non-zero pair of constants? At least one pair of non-zero constants to make that thing zero? Yeah. Which means, which case are we in by definition?
The dependent, literally.
Dependent, all right? If you can find non-zero, if you can only find zero constants, all right, then it's linearly independent. All right, so hence the system is linearly dependent. All right, let's do that again. All right, and this last statement, all right, that's why I'm being real specific here, all right, to make sure, again, including everything. All right, we found at least one set, right, satisfies the definition to make it linearly dependent. Now, notice this one. I was like, I plug them in, I gotta plug it into the definition. I take a look, see if anything can combine or do anything. I was like, how many constants do I have?
3.
Two. T is not really constant,
Or
that's
two.
a variable, right?
Okay.
So, but 2 constants, how many equations do I have? Is there an issue there? Yeah. So, all right, a common technique in order to create, I need a second equation, all right, at minimum to help me get through this. Because yes, you're right, I have 3 things I'm trying to figure out. I got this variable that's unknown, then 2 constants I need to plug in. Okay, so I got way too much going on. So I need at least a second equation so I can maybe find a relationship between C and K. All right. So if this is a static equation, what's the best way to make a second equation?
So move that KT over to 0, like plus KT forward.
Oh, you're absolutely correct. But I need a second equation. That just moves this equation. This is a static equation. How about a dynamic equation?
Where it's not equal to 0?
What? No. I was like, static, right? Algebra. Dynamic is then what level of math?
Calculus?
Yeah. So what do you think I should do?
Integrate this thing.
Oh, other way.
Derive.
Derive. Yeah. Integrate is correct, but it always gets worse. Derivatives are usually pretty quick.
Okay.
I was like, yeah, but I was like, how about we just take a derivative? And that's actually a really fast way to create a second equation in algebra. I was like, if it leads anywhere is not always no. Okay. But it's like, it's like just the common technique of, hey, all right, so let's take a derivative. And then absolutely what you were saying, Josh. Now I have 2 equations with, again, 3 unknowns, but 2 that definitely need work. So I lost my K. So now I have 2 equations with at least 2 unknowns. And then let's solve this one and plug it into the other one. So but either way, be the same. All right, bring it over, divide by 4t. We'll get something that looks like this. Plug into our initial equation.
Why is that negative?
You're absolutely correct. All right, so I can algebraically solve this guy down to here. So what value of K makes this equal to 0 that is non-zero, right? Pick a value of K that solves this. It's not 0.
I don't think it's possible.
I was like, there is no solution here. T to the 4th, this is bouncing all over the place. I was like, this is a variable and I can't make this like the only way this works is 1 over T to the 4th. I was like, actually, no, actually that doesn't work either. 1 over T to the 4th doesn't even work because that just makes it 1, negative 1 equals 0. It's still bad. The only thing that plugs in here is 0. All right, which means this is the case that I couldn't figure that out. And since C equals negative KT squared, only K equals 0 and C equals 0, solve the equations. So solve C. That's f of x equals 2t squared. To the fourth are linearly independent.
Do we keep it as x even though it's a function of t?
Oh, jeez, you're right. Did it write f of x?
Oh, yeah.
Oh, no, I did right. Definitely. Okay. I was like, yeah,
Where at?
and that one was x and that one was
Oh,
t.
no, I see you now. No, I see.
Yeah, but you're right, it's t. I was like, whatever it is, but yes, we bounce back and forth. X is.
Some of the home funds, I made the mistake because like the
Oh,
identity is p to the t,
Me
dt.
too, 100%.
And I went through, I was like, oh no.
Okay,
So this is linear independent. Would that be a part of the answer too? Sorry about that. Okay.
and hence they are linearly independent. Now, be aware, the biggest part of these is identifying linearly independence can send you down the rabbit hole for a lot longer than dependence. It's usually easier to spot dependence than independence because you have to make absolutely sure there is no possible non-zero combination. This is where the Wronskian comes in. All right. If the Wronskian is not equal to 0, the functions are linearly independent. So actually it takes away our hardest case.
Cool.
Because doing the Wronskian not equal to 0, boom. All right. If it's not equal to 0, then they're linearly independent. Now be aware what this does not say. Notice the other fact. If they're linearly dependent, the Wronskian equals 0. This is not if and only if. Okay? It does not say if the Wronskian is 0, they are dependent. Which means that if you get it non-zero, boom, they're linearly independent. If you get it equal to, if you solve the Wronskian and you get 0, what do you have to do?
Let's go back and do this process.
Do that definition, okay? Because it is very possible that it equals 0 and they are still linearly independent, all right? That sucks,
Yeah.
okay? So there are still cases here, but hopefully, all right, the idea is if you get 0, most of the time they're dependent, so you're really looking for that possibility of C and K. But it is still possible that they end up 0.
In your opinion, what's that percentage of like?
Low.
Okay.
Low. Like, I was like,
And I'm not sure of any of the cases that we did.
like, or will do.
So it is pretty rare to.
It's pretty rare, but possible.
It
It's
exists.
super important. My point is to formally prove it, you don't say, oh, it's 0, they must be. And that's not what this definition says. It says that you need to do another step. All right, to that end, let's see if we can do these a little quicker using the Wronskian. So here's the one we already proved, right? We already proved actually both of those. Okay. And so basically this, when I do the Wronskian, I do the Ronskin, I get it equals 0. The best we can say is the functions may be linearly dependent. All right, but we didn't prove this earlier. But it's the important part is I want to make sure, right, that we understand with the Ronskin, the only conclusion I can make if I get it equal to 0 is they may be linearly dependent and I need to keep going. But we did already do this. The good news comes when we identify things that are independent. So this one, when I do the Ronskin, I get 4t to the 5th. Where's 4t to the 5th 0?
At the origin, 0.
Yeah. All right. So, all right. This one we need to quantify a little bit, but. And this one we also proved earlier as well. Okay. So typically, all right, this one needs quantification because this can be 0. All right. So don't just be like, oh, it's not 0 ever. All right. So make sure you're thinking about the domain. And sometimes initial domains are given. All right. These functions didn't have any initial domains because that's a parabola and that's whatever to the 4th power. All right. So both these can be 0, right? They're not like initial domain restrictions like we saw even on those other ones we proved. All right, one more. Function 6x and 6x plus 2. So just fun recall, when I take the derivative of a power to an x, do we remember what it becomes?
So like the ln of 6 to the x.
Yeah. I used to say 6x ln of 6. But yeah, same thing. When we do this one, we would get the Ronskin equals 0, which means so essentially no information from the Ronskin functions may be linearly dependent. We need to prove it. And this actually breaks down pretty nicely. So 6 to the x, right? 6 to the x plus 2. What might be helpful there? With 6 to the x plus 2.
Like 6x times 6 squared.
Exactly, right? Bring that exponent across, because actually I'm going to have something a lot easier to solve if we do this as k times 6x times 36 equals 0, which means I have c 6x plus 36k 6x. Just like e to the x and every other equation, where does 6x cross 6 to the x cross 0? It does not, which means I can actually pull that thing out. Which means I have this equation, and I see pretty easily. Can we pick a c and a k?
Yeah.
Specifically? Oh, yes, okay. What do I have to pick? Because I picked one here.
Oh.
No.
If
I feel like you did not pick the easiest, not difficult. But
Oh, you're gonna equal to 0. Oh,
negative 136.
yeah, that's pretty.
I was like, did not pick the easiest in my opinion. The easiest is negative 36 and 1. But are there lots of options? Absolutely. I don't care what you pick. If you pick decimals, of course. Like I was like, because he said 1. So I was like, oh well, we're here. We can figure it out. So, all right, as soon as you pick a non-zero value,
Is it either they're both 0 or both a number, or is it possible to have one be a number and one be
I was like, the thing is like when you solve it, sometimes you can get 1 equal to 0, because if you can write 1 as a function of another, I was like, but they both can't be non-zero. That's the idea. But I have seen where 1 is 0, but definitely not both.
Okay.
I was like, so yeah, be aware of that. That is a good point. Because I've solved it where I was like, I found 1 to be 0, but the other was not. And it like satisfied it. Because mostly I could write 1 as a function of the other. But when you go and pick those constants, sometimes you'll get 1 of 0. But it's usually because 1 is a function of the other when you wrote it.
okay.
So it's kind of like what we ended up in that independent case, but actually I can figure out a value.
Okay.
Okay, so we found a non-zero, so okay, satisfy this. So f of x equals 6x and g of x equals 6x plus 2 are linearly, I forgot, independent?
Dependent.
Oh, dependent. So it's super important to make sure we get that right.
So if I forget I forget the guy's name.
Ronskin.
If the Ronskin 0, always do a double check.
Oh, 100%. No, you need to use the definition, right, in order to satisfy this. Okay, we are so close to the end that I want to finish this, and we'll try and get out early next week. Okay, we're only going to take 10 more minutes. The other theorem, so Abel is a shortcut theorem that actually is basically a workaround for doing the full Wronskian. It's really just a constant e to the basically the integrating factor that we're super familiar with. All right, you take the PT function and you can identify the Wronskian now within a constant, which doesn't matter because the constant is by definition non-zero, and we're just trying to identify if it's equal to 0 or not.
Why is that negative?
This one, because that's the definition of the Wronskian with Abel's theorem.
Okay,
All right, and it has to do with usually the determinant, the subtraction.
okay,
I
okay.
was like,
I was on PTSD. I was like, oh no.
this one is negative.
Okay.
I said it's like the integrated vector. It's not exactly. That's super funny though. So, all right, let's see if we can use Abel's theorem to find the Wronskian in these couple equations. All right, as with everything, this is about the form. Okay, so notice the form in order to use Abel's theorem. All right, and notice the form we're given sometimes. What do we have to adjust? All right, on A.
Double prime needs to be by itself.
Yep. And the form is, again, a simple form, but a very common one. We just need to divide this whole thing by t to the fourth. And then we can use Abel's theorem. Which gives us C equal CT squared. And this is the nice thing, all right? We can get this within a constant of what the Wronskian is. So this would be, almost like, if I'm trying to compare it to not equal to 0, I'd have to say, once again, as long as t is not 0, the Wronskian is not 0. But the idea is that with a simple integration, as long as it's not too complicated, all right, it depends how difficult that function p of t is. But I can do this integration instead of doing maybe what is annoying, 2 derivatives and then a determinant of 4 functions. Let's see one more. This one, all right, we actually already found. Since we're in the right form for Abel's theorem, and this one, actually I can determine, does this ever be equal to 0? Nope. And this is exactly, right, we found that one, all right, above.
Yes.
Okay, we found that previously, way further up the notes. But this one, right, found earlier. And we can see that the Wronskian does not equal to 0, is not equal to 0. So what's nice is, oh, this is clearly a fundamental set of solutions, and I can prove it really, really quickly, all right, with Abel's theorem. That's the benefit. Which one you use kind of bounce back and forth, depends how much you're feeling like integrating versus doing it. But either is completely appropriate.
Is there ever context of one's preferred over another? Like a style of function or a style of problem or?
I mean, usually when I set it up, if when I get it in this form and this looks ugly, then yeah, I'm gonna take derivatives over integrals in an exponent.
Okay.
So it's really just a judgment call. Like, I was like, most of the problems I don't identify. Occasionally I say, hey, use Abel's theorem to do this just to make sure because most people get in the habit of doing it this way for the obvious reason that we're way more familiar with determinants. Actually, we're just used to doing determinants, and it's this one's super easy to remember. Even Abel's theorem, I have to remember the negative gets me too. I'm like, I have to make sure I put the negative on there. But this, two functions, two derivatives, determinant. This I can do over and over. But if this starts getting ugly, when you go to actually solve this, then think about Abel's.
Okay.
That's usually the idea. But is there a right or a wrong? No, it's just how much can you take the algebra in one case or the other?
Sure.
All right, that is absolutely everything. All right, for chapter 3.